This short video is on volume problems. These are stoichiometry problems, all right, in which we're given initial volumes and we're asked to find the volume of the final volume of a container. And they're assuming a lot here that's not written into the problem. The first thing they're assuming is that the reaction is going to go to completion. This is highly unlikely when you're dealing with gases in the container. So later on, we're going to throw some equilibrium on top of this stoichiometry, but we'll talk about that later. But for these problems, they're going to assume completion, and they'll write the word completion, which means whatever the limiting reactant is, it's completely consumed. The second one, which is a little more, probably more important in dealing with the actual question, is the idea that you're dealing with a non-rigid container. If it was a rigid container, we'd be dealing with changes in pressure. Since it's a non-rigid container, and you kind of have to visualize this, what this is it is a piston. So you assume you have a gas A that's in a container. Let's say this is a 20.0 liter container. Let's say the gas A is, it's filled with hydrogen, one of the two gases that are a reactant here. We assume that the gas A is pushing up on the piston with a certain amount of pressure, and that the atmosphere is pushing down with a certain amount of pressure as well. And they're at equilibrium. So the pressure of the atmosphere is equal to the pressure that's being caused by the gas contained within the piston, within the cylinder or whatever, the space. All right. And the idea is that if we take these two separate volumes of hydrogen and nitrogen, they take these two and we put them together into another container, the assumption is that other container will have a volume of 40.0 liters total. We can make that assumption because if they're under the same conditions of temperature and pressure, we can use Avogadro's principle. Okay, and this is also key in terms of making the math easy for you. You can do this in a very complicated way, or you can realize that the number of moles is proportional to the volume, assuming that the pressure and the temperature remain constant. In other words, you have a certain number of molecules of nitrogen. Since the volume of hydrogen was exactly the same, the number of molecules of hydrogen you had was exactly the same. So when you double the number of molecules in the container at that temperature and that pressure, the volume actually doubles. Right? It doesn't matter that one's hydrogen, one's nitrogen. You just put X number of molecules in the container with X number of molecules of the other gas in the container. So now you have 2X molecules, twice as much volume as well. That's what Avogadro is really talking about. And that makes doing stoichiometry with gases actually kind of easy, because you can assume that the mole ratio is the same as the volume ratio. So you can say, and you can just do a very simple limiting reaction problem. So you've got, for every 1 mole of nitrogen, you're going to have, let's say, 3 moles of hydrogen. And so you can do this and you'll get, okay, well, if all 20 liters of nitrogen react, I would need 60.0 liters of hydrogen. That ain't happening. We know now that this right here is going to be our excess, just like we've done in the past. And we know that in terms of our hydrogen, we know for every 3 moles of hydrogen, right, we're going to need 1 mole of nitrogen. And so we know at the end of the day, 1/3 of this is going to be 6.67 liters of nitrogen. So we know how much of the nitrogen is going to be consumed. So we can do a little bit of quick math here, right? We're going to have, at the end, we're going to have 0.0 liters of hydrogen because that's our limiting reagent. We can do 20.0 minus 6.67. I should have put more zeros here just to make the question a little better. So let's assume it goes out to the hundredths place here, right? So I can go 20 minus 6.67, and that gives me, so I've got 13.33 liters of nitrogen remaining. And I can choose to do the other part whatever way I like. I kind of like the idea that since I can only use the 6.67 liters of nitrogen that's consumed, because basically I can do a 1-to-2 relationship. So I go, for every 1 mole of N2 that's consumed, I'm going to make 2 moles of ammonia. So I can just take my 6.67 and times it by 2, and that also gives me 13.33 liters. So I'm going to have 13.33 liters of ammonia. And the assumption is because when you're done with this reaction, there'll be less. Now, if you think about this, right, the reality is we now have less molecules in the container. That's why the volume will be smaller. So the final volume here is going to be 6.67-ish, something like that. And what that means is because there's less molecules in there and the pressure of the atmosphere really has not changed at all, okay, and since there's less molecules, the pressure on the gases inside is going to be less than it was initially, and so this volume is now going to change, and the piston is literally going to move down until the pressures are once again equal. When will they be equal? Well, when the number of molecules is in a smaller amount of space, basically. At that point, they'll reach equilibrium again, and when they reach that equilibrium, they will be 26.67 liters of gas in the container. So, really quick summary here. The basic ideas are the reaction is going to completion. You've got a non-rigid container, and you can literally use the coefficients in the reaction to determine the changes in volume of the individual gases, and that's only because it is a non-rigid container and because of Avogadro's idea that the volume is proportional to the number of molecules that are in the container.